Yeah, hi everyone. In this particular video, we will try to understand one of the important transport layer protocol called TCP. TCP stands for Transmission Control Protocol, which is a connection-oriented transport layer protocol. We will be trying to understand its segment structure, then the reliable data transfer, how do we implement flow control in TCP, and what are the connection management mechanisms of TCP. The next sessions will be talking about congestion control, the principles of congestion control, as well as the TCP congestion control mechanisms. Right. Let us have an overview of transmission control protocol. The technical names of TCP are RFC 793, 1122, 1323, and so on. And we know that RFC stands for D for cont. Now coming to the main features of TCP, the first and most is TCP is a point-to-point connection-oriented transport layer protocol. So between the sender and the receiver, a point-to-point connection is established before the data is transmitted. And since it's a connection-oriented, all the data flows in one direction in order in which it has been generated. And the flow of data is a stream of bytes. So since it's one after other, we need not have any boundaries between the two segments. All the segments will be of uniform size. Then we also implement a pipelining concept where we are trying to ensure we can send multiple segments before we wait for acknowledgement, and also there should be a flow control and congestion control mechanisms adapted so there is no loss of data. And to implement the flow control mechanism, we are using certain buffers at sender as well as the receiver end. The flow of data in TCP is full duplex type. So what do we understand by full duplex? The data flows in the both directions and also at the same time. And the maximum data that can be carried by a segment will be referred as maximum segment size. And as I already mentioned, TCP is a connection oriented protocol. So before the data transfers, a connection has to be established, for which we use certain handshaking mechanism. Later is followed by a data transfer, and finally after the transmission of data, the connection will be terminated. So we have three phases: connection establishment, then data transfer, and connection release. So totally these three are referred as data transfer and connection release. And as we mentioned, we have the flow control mechanism. So sender will not send any beyond the capacity data that will overwhelm the receiver's buffer size. So this is a quick overview of TCP and its future. Right. Now let us look at the segment structure of TCP. The data format in transport layer is referred as segment, and we are talking about TCP segment structure. The first row of a TCP segment consists of the source port number and destination port number. We know that the transport layer is responsible for process-to-process delivery, and to implement process-to-process delivery, we use the port numbers. The process which generates the data is referred with source port, and the process to whom you are delivering is referred with destination port. Every segment having a set of bits, the starting bit number of every segment is referred as its sequence number. For instance, my first segment is carrying 100 bits of data, and it means 1 to 100, and second segment is going to carry from 101 to 200. So here the starting number of every segment is referred with its sequence number. And when I am receiving my first segment of 100 bits, and my next expected segment should start with 101. So I will acknowledge the 100 bits, and I mention that I need a segment starting with the number 101. And for that we are using acknowledgement number. In the third row we have the first field called header length, which is of length 4 bits. It is trying to indicate the length of TCP header. There are no options adapted by the TCP, then the length of TCP header is 20 bytes. The 6 bits are reserved here, and then we have 6 different flags used by TCP. If there is an urgency of data to be transmitted by the sender, it indicates by saying that U equal to 1, and whenever receiver receives the data, it has to immediately transmit the data to its upper layers. The next field is called acknowledgement. As we mentioned, Acknowledgement indicates two purposes. One is successful reception of previous bits, and second is the expected bit number of next segment. And push field is used when we want to push the data which a receiver receives into its upper layers. Whenever a push operation is required, the push field in your sender is set to 1, else it will be 0. And the remaining 3 fields, which are reset, synchronous and finish, are used for connection establishment and connection release. So we have already mentioned that TCP implements flow control and congestion control, and for this we use a window called receiver window. And the next field is checksum, which is used for error detection and error correction. An urgent data pointer is being used whenever the value of u equal to 1. So when u equal to 1, the data to be transmitted is mentioned by the urgent data pointer. So various extra features which you want to adapt are mentioned by the options field. And then the application data is the length actual data which you want to carry along with that particular TCP segment. So TCP segment consists of header and data, and all these fields are indicating the header part. There is no options. The header length is 20 bytes, and it is followed by options, followed by the data to be transmitted. Right. In the previous field, we were talking about sequence numbers and acknowledgement numbers in the TCP segment. So the sequence number indicate the first byte of a segment. For instance, in this case, host A would like to communicate with host B. So the first byte of the segment which is sent by host A starts with a byte number 42, and the data carried is mentioned by C, and probably it has previously received from B with it has been receiving with 78 byte number, so it's acknowledging 79. Now host B, once it is receiving that particular segment which is starting with 42 and acknowledgement number is 79, so now it sends a byte or a segment which starts with a byte number 79, and also it has received a data with a sequence number 42, so it is going to acknowledge with 43. And when host A once again receives this segment, it has received a sequence as a segment with a sequence number 79, so it sends an acknowledgement of 80, and since the previous acknowledgement is 43, now it is sending the segment starting with a byte number 43. So this is the importance of sequence numbers and acknowledgement numbers in TCP transmission. Right. We know that whenever a TCP sends a segment, it immediately starts a timer, and before the timer expires, it is expecting a acknowledgement to be received. Fine, but how much time should the TCP wait before it waits for acknowledgement or retransmit the same segment? The total time taken for a segment to move from sender to receiver, and again the acknowledgement come back to the sender, we call this time period as round trip time, RTT. So with that, this RTT time should be as low as 1 minute or 1 second, or it should be too long. So what should be the ideal time to set for a round trip time? So that will be the time which we set in our timer to wait for the acknowledgement. Well, in our previous slide, we were trying to understand the round trip time is the total time taken for a segment to travel from the source to the receiver, and to come and acknowledgement to come back from the destination to the receiver to the source. So the timer value which we set for our timer value which we set, we refer it as timeout value, so that once this timer expires, we have to retransmit the same segment. So how should we set our timeout? Generally, it should be the timeout values must be longer than the round trip time. But round trip time is varying, depends on various factors. If we try to keep your timeout very short, what happens is there will be premature. What it means is before we receive the acknowledgement itself, the timer gets expires, and unnecessarily we have to retransmit the same segments. So there will be more unnecessary retransmissions if we are using too short timeout value, and if it's a too long value for the timeout, even though we receive the acknowledgement, still the timer does not expire, and our transmission will be very slow. So too long timeout is not suitable. Too short timeout is also not suitable. So how do we estimate the timeout value? For this, what we try to do is we will try to take sample round trip times. So sample round trip time is a time which is measured from segment transmission until the acknowledge received. And maybe for each instance, the RTT may be a bit variable. So instead of taking one sample, what we are trying to do is we are taking some 3 to 4 set of different RTT times and average of the recent measurements so that we can get an accurate picture of an average what will be the round trip time for the transmission of data. Right. Earlier we were discussing about estimating the timeout value based on various sample round trip times. So let us have a look at how to estimate the round trip time. So the estimated round trip time we are using something called as exponential weighted moving average method. What is this? For instance, I take a reference of last 4 values. For instance, I am at 1, 2, 3, 4 and I will be taking this 4 reference values. But if I have a new value, this 5th one, then I will ignore the first value and I will now consider only 2, 3, 4, 5. So we are going to adapt exponential weighted moving average values, and here the estimated round trip time is calculated using another constant called alpha, which is in general used equal to 0.125, and using this alpha and our estimated RTT, we measure estimated RTT equal to 1 minus alpha times that of estimated RTT plus the alpha times that of sample RTT. And by adapting this method, the influence of past samples decreases exponentially and fast, and we will be able to get a better closure value. Right. In our earlier, we were discussing about how to estimate an RTT value using the alpha and sample RTT. Now this is a plot which is indicating the relation between the sample RTTs which are highlighted in the blue color and the estimated RTT which are highlighted in the pink color. So using a constant alpha and also the values of the sample RTT which are being indicated in blue, we are estimating the round trip time. This value is called estimated RTT. Right. So in our previous slide, we tried to determine the estimated RTT from the sample RTT as well as the constant alpha. Now, once we have determined estimated RTT and we also know the recent sample timeout values, then we are trying to set your timeout value which is greater than this estimated round trip time. The difference between them we will be referring with a term called safety margin. So how much addition time should I set for my timeout compared with estimated RTT, which is called as safety margin? To determine that safety margin, we are determining a parameter called deviation RTT. Now, what is a deviation RTT is? It is indicating how much the sample RTTs are differentiated from the estimated RTT. And the formula to calculate deviation RTT is 1 minus beta into deviation RTT plus beta into sample RTT minus estimate RTT. So we already know the sample RTT and estimated RTT, and one more value which we are considering is beta. So we have only one unknown which is deviation RTT, which can be determined using the relation between deviation RTT, sample RTT and estimated RTT. Once we are able to determine the value of deviation RTT from this, the next thing we try to do is calculating the timeout interval, which is the time which we set for our timer, so that immediately after the timer expires, it will be retransmitted. And that timeout interval equal to the estimated RTT which we determined from the previous slide and plus the 4 times the deviation RTT which we are calculating using the above relation. So finally we are able to calculate the timeout using TCP round trip time, from which we are calculating estimated RTT, and to that we are adding a safety margin of 4 times the deviation RTT. Right. So far we have understood about what is the TCP and the features of TCP. The previous we were discussing about TCP segment structure and how to estimate the timeout values. Now let us try to understand how does a TCP implement reliable data transfer. Right. So the reliable data transfer provided by TCP. Here, TCP creates reliable data transfer on the top of Internet Protocol's unreliable service. We know that Internet Protocol is providing only unreliable best effort delivery. So the TCP tries to create a reliable data transfer. It is supporting pipeline segments. It is sending cumulative acknowledgements. The pipeline segments is a case where we are trying to send multiple segments before receiving the acknowledgement. And instead of sending many acknowledgements, we are trying to send a single cumulative acknowledgements acknowledging all the previous received segments successfully. And also we'll, instead of using a timer for every transmission, we can also try to use a single retransmission timers. Generally, when do you find a retransmission in TCP? When you send an acknowledgement, when you send a segment, you started a timer, and before the timer expires, if it doesn't receive the acknowledgement, that are called as timeout events. In second case, when we send your retransmission is when we receive the duplicate acknowledgements for the previously sent segments. So initially, let us consider a simple case where we don't have any duplicate acknowledgements. We ignore the flow control and we also ignore the congestion. Right. If we, for instance, we will try to observe what are the different activities that are happening at the TCP sender. Simple. At the sender side, the transport layer is waiting for receiving the data from application layer. The moment it receives the data from the application layer, it creates a segment with a particular sequence number. We know that sequence number is the byte stream number of the first data byte in the segment. And once the segment is ready, it will be transmitting the segment to the network layer, and then it starts the timer. If it is already not running, we'll start a new timer. If it is already running, we have been continuing our transmission. So we said that here we'll, instead of using multiple timers, we'll try to use a single timer. Right. So we will be sending the segment, start the timer, and before the timeout event occurs, we are expecting to receive our timer, our acknowledgement. In case if it doesn't happen, then we are going to retransmit the same segment. Right. In case if we are receiving a positive acknowledgement, then in that scenario, we will update the segments which we have already acknowledged, and for the next segment, we will be sending with the segment with the sequence number equal to the next expected byte number. And in case if your timer is already expired or been closed, we will be once again starting a new timer. Right. So let us try to look at the discussion in terms of a simple algorithm. So initially we will set our base sequence number, which is our initial sequence number. For instance, I start with byte with sequence number 1, and my length of byte is 10 bytes. So here I want to send a segment starting with the sequence number 1 and length is 10 bytes. So once I am trying to receive the data from the application layer, I am converting the data into segment with a sequence number equal to 1, and the length of my segment is 10 bytes. So here, after sending the segment, I will start my timer and the segment is forwarded to the network layer. And since my initial number is 1, length of data equal to 10, the next expected sequence number should be 11, because already the first 10 bytes have been transmitted by segment number 1. Now before the timer expires, if we get a positive acknowledgement, then definitely we'll try to send the second segment with a byte number or a sequence number equal to 11. But here, in case if there is a timer timeout, still we did not receive an acknowledgement, we are going to retransmit the same segment 1 starting with a byte number 1. So positive case, we will be sending the next segment with a byte number 11. If it is an retransmission case, we will retransmit the same segment 1 with the sequence number 1. Right. Let us now look at different retransmission scenarios in the TCP. Here, the first case is lost acknowledgement scenario. A host A will be trying to send a segment with a sequence number 92 and if the length of segment is 8 bytes. So the host B, which is the destination of the receiver, received it successfully. So it's want to send an acknowledgement 100 indicating that it has received the first segment of length 8 bytes starting with the sequence number 92. Unfortunately here you could find that acknowledgement has been lost. And whenever a host is sending a segment, it started a timer, and by this time the timer has expired, the timeout scenario has generated, but still the acknowledgement is not received. So the host A, it will be retransmitting the same segment with the sequence number 92 of length 8 bytes. The receiver, after receiving it, may understand that maybe that host A did not receive the acknowledgement, so we'll once again retransmit acknowledgement with a sequence number 100 indicating the next segment expected is the sequence number 100. The next scenario is a premature timeout. How do we understand a premature timeout? We have discussed earlier when we are keeping a too small timeout value before we receive the acknowledgement, the timer expires and we retransmit the data unnecessarily. Here you could find we have two cumulative segments, segment from host A. The first segment with sequence number 92 and length is 8 bytes, and second segment is with the sequence number 100 and length of data is 20 bytes. So on reception of this both segments, the host B has sent two acknowledgements separately. The first acknowledgement indicating that it received the first segment with sequence number 92 and of length 8 bytes, and it received the second segment with the sequence number 100 and length is 20 bytes, indicating my acknowledgement number of next byte segment expected is 120. But here, since your timeout value is very small, before we receive the acknowledgement of first segment, the timeout has expired and we have retransmitted the first segment. So what is being understood here is, though the packet is segment is successfully transmitted and the acknowledgement is received, since we have kept a low timeout value, unnecessarily we have implemented retransmission, and when the receiver received again the same segment with the sequence number 92 and 8 byte, instead of sending two separate, it sends a cumulative acknowledgement indicating already I have received all the data up to 120 bytes, and next byte for the next segment which I am expecting is with a byte number 120. Right. So here the host A is sending two segments, which is called pipelining segments, and the first segment is with sequence number 92 and length of 8 bytes, and second segment is of sequence number 100 with length of 20 bytes. So here there is also the B, which has received those segments, has sent two acknowledgements, but you can see here the first acknowledgement is lost, but second acknowledgement is transmitted successfully, and though we are not retransmitting, but still the sender came to understand that till 120 all the segments and the respective bytes are being received successfully. So there will be no retransmission. So here this acknowledgement will be acting as a cumulative acknowledgement. Right. Now let us look at the different acknowledgements generation scenarios at the TCP receiver end. For instance, the first case is where everything happens positively, and here you find we are receiving a segment in an order with the expected sequence, and all the data up to the previous expected sequence have been already acknowledged. Now I have already sent acknowledgements for the previous segments. Now I received the expected segment. So what should I do? It's simple. Just wait for few seconds, that is up to 500 milliseconds. Maybe you get the next segment, and instead of sending two separate acknowledgements, you can send a cumulative acknowledgement. But if you don't receive any new segments, you can send the acknowledgement. So if you are receiving in order, wait for a few seconds so that there may be any immediate followed segment, else you can send the segment for the received segment. The arrival in order segment with expected sequence number, and we have one of the previous segments which are pending. So here it's a simple case where you can immediately send a cumulative acknowledgement indicating all the segments which are expected have been already received. In case if you are receiving a segment out of order. For instance, I'm expecting 120 but I'm receiving 150. Immediately you have to send duplicate acknowledgement saying that, boss, I need a segment with a sequence number 120 but not 150. So that you will receive only that segment with a sequence number 120. So in case if any of the segment that is trying to partially or completely fill the gaps, then immediately send acknowledgement, provide a segment starts with at the lower end. So these are the different ways we handle our acknowledgements. Right. The next and most important, one of the most important topics in our discussion is called as fast retransmit. So try to understand the term that is fast retransmit. When we are going to implement the fast retransmit. A fast retransmit concept is simple where we are trying to retransmit the same segment before the timeout occurs. So what are the scenarios that is leading for the fast retransmit? Let us try to observe. So generally, in case if you are setting your timeout period to be too long, if your timeout period is very long, and unless the timeouts, we generally do not reset the same segment. So in that scenario, if you are detecting the lost segments, for instance, I sent 3 segments, segment 1, segment 2, and segment 3. If my segment 1 is lost and my segment 2 and segment 3 are received by the receiver, it will send a duplicate acknowledgement saying that, boss, the sequence or the segment number I am expecting is 1, but I am receiving 2 and 3. So whenever we are receiving 3 consecutive duplicate acknowledgements, even though the timer is not expired, understands that particular segment is lost and you have to retransmit the expected segment. So retransmitting an expected segment before its timeout occur, we refer with a term called fast retransmit. Let's look at the pictorial representation of fast retransmit. For instance, here we have multiple segments and the first segment is being transmitted and has been successfully acknowledged. The second segment has been transmitted but it has been lost during the transmission, and segment 3, 4, 5 are successfully transmitted. But since the receiver is expecting a segment with sequence number 2 but it is received segment with sequence numbers 3, 4, 5, it will send a duplicate acknowledgement saying that, boss, I need a segment with sequence number 2. So when you receive 3 duplicate acknowledgements, though the timer is not expired, we are going to retransmit the segment. Retransmitting a segment before its timeout scenario, we refer it to called fast retransmit concept. Right. So this is the fast retransmit algorithm. So we have an expected sequence number, but if we are receiving duplicate acknowledgements, try to count the number of duplicate acknowledgements. For the first duplicate, second duplicate, no action is initiated. But if total number of duplicate acknowledgements received is equal to 3, so you have to immediately retransmit the segment irrespective of its timeout value. This particular concept is called fast retransmit, and the algorithm which we are mentioning here is called fast retransmit. Right. Earlier we were discussing that TCP not only implements a connection oriented transmission, but it also implements flow control as well as congestion control. So now we'll try to understand how flow control mechanism is implemented in the TCP. Right. One more important function which is performed by TCP is referred as TCP flow control. So we know from our earlier discussions that flow control is a mechanism where the sender won't overflow the receiver by transmitting too much or too fast of data. So how are we able to implement this using TCP? How does the sender know how much of the data has to be transmitted? Let us try to observe. So we were discussing that in this TCP, both the sender and the receiver are going to have the buffer. The capacity of the receiver buffer is indicated as RCB buffer. And let me tell you, sometimes what happens is the data is received by the TCP receiver buffer, but that may not be accepted or forwarded to the application process which will actually deal with the data. There may be certain delay there, because of which some data is still stored in the receiver buffer. So what is the total new data which we can receive and store in the TCP receiver buffer is indicated with a size called receiver window, which is nothing but the total receiver buffer size minus the amount of data which is stored in the buffer, which has been received by the TCP but not yet read by the application process. So this value is TCP receiver window, and normally what happens is whenever the sender has to transmit the data, the total data size should not exceed this receiver window size. So we are making a speed matching service, matching the sending rate of the sender to the receiver window size. Right. So the TCP receiver window size is calculated using the formula total receiver buffer minus the last byte which is received by TCP minus last byte which is read by the application. For instance, I have received 90, but application has wrote it only up to 80 bytes. So how many bytes are still here inside the TCP receiver buffer? 10. And if my capacity of the receiver, total receiver buffer is 100, out of which 10 bytes is occupied by this data, so the receiver window will be announcing that I am ready to receive only 90 bytes of data. And receiver advertises this spare room value in the receiver window size, so that sender, when it is trying to send the data, will not exceed the total length of data greater than the receiver window size. And through this particular process, we are able to ensure there is no overflow, and we are able to implement flow control successfully in the TCP. Right. So far we tried to understand what is TCP, the features of TCP, then the TCP segment structure, calculation of TCP timeout and round trip time, then what is reliable data transfer, and how do we implement flow control. Now let us look at how do we implement this connection oriented data transmission, and this particular thing is referred as connection management. Right. In the beginning of TCP, we have mentioned that TCP is a connection-oriented protocol in which there are three phases, that is connection establishment, data transfer, and connection release. So before a data has to be transmitted, a connection has to be established between the TCP sender and TCP receiver. So let us try to observe how a connection is established between the sender and receiver before the data is transmitted, and also we'll observe what are the things that are the process involved in closing the connection which has been established. Let us look at TCP connection establishment process. So before this, let us try to make some initialization of the variables which we are going to use. So we are going to initialize the variables like sequence numbers, the buffer sizes, and flow control like what is the receiver window size. All this has to be set. And the device which is trying to connect itself with others, particularly like servers, we call them as clients, and he is the one who will be initiating the connection request. And the device to whom the connection request is made, we are referring it as server, and it will be trying to wait or to listen the request from the different clients. So your server is in the listen mode and your client is in the connect mode. So what is the connection establishment process? So there are three steps involved. For that reason, this method is popularly referred as a three-way handshake mechanism. So initially, the client uses one of its flag, which we discussed in the TCP segment structure called as synchronous. The client host will send a TCP synchronous segment. So here you could find a TCP synchronous segment has been sent from the client host to the server host. And when the server host receives this TCP synchronous segment, it responds with synchronous acknowledgement segment. Here it will try to indicate the sequence, its initial sequence number also. And also that server will allocate certain buffer space. And once your client host receives that synchronous acknowledgement, then it will try to send the acknowledgement. Sometimes we also include the data along with that acknowledgement. So, right. In the previous slide, we were discussing about how a connection is established between the client and the server. Now, after the connection establishment, the data transfer begins and all the data will be transferred between the client and the server. And after the completion of the data transfer, there will be connection release phase. Let us try to look at the different steps which are involved in closing of a connection, for which we are using command called close. So when all the data which is expected to be received or transmitted by the client is completed, the client and systems sends a TCP finish, which is also one more flag of your TCP. So TCP finish control segment to the server. Let me tell you, this is only one way of or one direction of ending, but still the connection is not completely closed. So it says that from my end, I have transmitted or received all the data and I would like to finish the connection. And when the server receives that particular finish, it will send an acknowledgement saying that yes, I have received your acknowledgement. So now it sends a finish command from its end. So initially the finish command is from the client to the server, which it has acknowledged, and now the server is sending a finish command to the client and enters. Client receives this finish, it replies with acknowledgement, enters time to wait, will respond to this finish command from the server by sending an acknowledgement. The server receives the acknowledgement and connection is closed from it end, and this is a two-way closing of connection between the client and server. So previously we were discussing about how a connection is established, at the same time how a connection will be closed between the client and server. So based on these two phases, both the client and server will have different life cycles. Let us try to observe first client and then we'll look at the server. First, initially client sends a synchronous request to the server and it waits for the receiving an acknowledgement. So whenever the server receives the synchronous request from the client, it responds with synchronous acknowledgement. And after receiving the synchronous acknowledgement, the client responds with an acknowledgement. With this, the connection is established between the client and server. Now next, the data will be transmitted between the client and server. And once all the data is complete, the client initiates the closure by sending a finish command. And now the client moves to finish wait state. And here the client will be waiting for the acknowledgement. After receiving the acknowledgement from the server, now the client is in wait for receiving a finish command from the server. And later it receives the finish command from the server and acknowledges it. And after waiting for a certain time, the connection will be closed. So what are the different stages of life cycle of a client? Initially sends a synchronous send, then receives an acknowledgement, it sends an acknowledgement and moves from synchronous send state to established state. After the entire transmission of data, it sends a finish, and moves to finish wait one state, it receives an acknowledgement for it, and then also receives an finish from the server, and finally after certain time wait, it will close the connection. So similar things happen at server end. Initially the server is in closed state. Now it receives a synchronous request from the client. So it responds with synchronous acknowledgement. And once received as synchronous and sending a synchronous acknowledgement, it moves to synchronous received state. And then here after receiving the acknowledgement for it, the connection is established and data is transmitted. So you move from synchronous received state to established phase. And after all the data is transmitted, the client sends the server finish request. So receives the finish request and it sends an acknowledgement. It moves to close wait state. And later it also sends a finish request to the client and it moves to the last acknowledged. And after receiving the acknowledgement from the client, it moves to the closed state. These two phases of our client and server are called TCP Connection Management, TCP Client Life Cycle, and TCP Servers Cycle.